One of the most important tasks that the auditory system does is help us locate the sound source. And so this helps us know where a person or object is using just auditory cues. And there are three ways that our auditory system does this. It uses three different types of cues. The first one has to do with a difference in intensity. And so here in this picture we have a demonstration, and the speaker is basically to the right of the listener, the recipient of the sound. As a result, the right ear is receiving the information, the auditory information, at a slightly louder volume, because we all know that as a car, for example, or an airplane goes away from us, its sound diminishes. And so this happens even at a really small level, just between the distance of the right ear in this individual versus the left ear in this individual. And so the right ear is getting a slightly louder sound. And so that creates a difference in intensity that the auditory system then uses to calculate the location of the speaker and determines that the location of the speaker is here. And if you remember, the superior olives in the midbrain play an important role in that by comparing the sounds that come into the left and the right ear. Another cue is really similar, and it's just the difference in the time of arrival. So the auditory system is really, really good at detecting tiny differences in the timing of sounds. And this is actually really important for speech perception, because the difference between, say, a D and a T sound is a matter of like 30 milliseconds. It's just a tiny difference. And so the auditory system is really good at detecting small differences in the timing of sounds, and as a result, it can tell that the sound arrives at this ear, the right ear, just a little bit sooner than it arrives at the left ear, and that creates a difference in time arrival. And that is also something that the superior olives calculate, and then that other areas of the brain are able to use to figure out where this object is. And if you remember, the where system relies on the parietal cortex in that dorsal stream that we saw earlier, allows us to figure out the location of a sound. An additional cue is called phase difference. To look at phase difference, we need to remember that sound waves differ in their frequency, right? And so different frequencies of sound, of course, correspond to different pitch. But what it also means is that the phase of a wave when it hits, say, this individual's left ear is different than when it hits this individual's right ear. On their left ear here, we're seeing it's on this rising phase, right? Going up. But when it hits the right ear, it's on the falling phase when it's going down. And so we can see a couple examples here where it's hitting the left and the right ears at different phases. And that is an additional cue for the location of a sound, figuring out which ear is closest to the sound. So all these three cues are all about figuring out which ear is closest to the sound and how close it is to the sound. So the distant ear's wave will lag behind the near ear. Because of that, the brain can sort of deduce the location of the person or object making the sound. Now this cue is only useful under 1500 hertz. So really high, higher frequencies of sound, it doesn't really help too much, just because as the frequency gets higher, the sound waves get shorter, right? Like they'll get smaller, and then it's possible that you can have a peak here, and then it goes up, down, up, down, up. And it's possible for it to hit the peak at both left and right ears at the same time. And that's just a function of the frequency being so high that the distance from peak to peak gets really small, so that it can repeat multiple times between the two ears, and then you lose the ability of phase difference to distinguish between an object to the left and object to the right. Now, how does this work? We have in the nervous system these neurons called coincidence detectors. And we're going to talk about this because this is useful in a lot of aspects of determining movement or location of objects. And so here we have a really nice example in the auditory system of these coincidence detectors. They detect when a sound arrives at the same time from both ears. And likewise, they'll also detect when the sound does not arrive at the same time. And what it does is we can see here in this picture that the right ear has a series of neural pathways that all connect with these different neurons. A, B, C, D, and E are the coincidence detector neurons. They're receiving inputs from the right ear and from the left ear. Now let's look at those inputs. The right ear has a short distance path to neuron E. And so this signal is going to get here pretty quick. In contrast, the left ear has a pretty long distance to go to neuron E. And therefore, it's going to take longer to get here. If the sound inputs arrive at neuron E at the same time, the brain then knows that neuron E is getting a signal that arrived at the left ear first. Why? Because that's the only way that the signal could have taken this long route to get here and still have arrived at the same time that it got here from the right ear, which only had a short distance. And we can see an example here, same thing with neuron A. If it arrives from both ears at the same time, then that means that the signal is here at the right ear, because that's the only way that the signal could have traveled all of this way through the neural pathway and arrive at neuron A at the same time that it arrived from the left ear, because the left ear only had this very short distance. So the only way that neuron A can get these two inputs at the exact same time is if the auditory input, the actual sound, arrived at the right ear first. Now what happens if the input arrives in the middle at neuron C at the same exact time? That means it's the same time to come from left ear as coming from the right ear. And that tells us that the sound source is directly in the middle. Finding the location of an auditory object is something that everybody does. But it is particularly important for certain species like bats and dolphins and whales, some birds. We use it in using technology in submarines to help locate objects without using visual cues. That ability can be enhanced when an organism or an animal or a person or an object emits a sound. And so I can't detect it myself because I'm not good at this, but if I snap my fingers and I'm sitting next to a wall, that sound that I'm making is bouncing off the wall and coming back to my ear. And that means that if I was good enough at this, I should be able to determine that there's a wall to my right just by doing that. And that is what echolocation is. It's when a sound that someone generates that bounces off of an object is seen, in the sense not that you see it visually, but that you can locate it. You can identify the object and locate it. And this is what has been found to happen in some individuals who are blind. So here's an individual. So this is participant EB who is blind. EB makes clicking sounds that bounce off of other objects and allows him to recognize when there's a tree or a car or another person or whatever it might be. And if you see here on this brain image, we have here the back of the brain. That's the visual cortex. And what we're seeing is that when EB echolocates, when he clicks and then perceives those sounds and uses it to detect the location of an object, he's using his visual cortex to do this. And the visual cortex is great for doing this because it naturally creates a map of objects in space. Now, normally it makes a map of visual objects in space. It's the visual cortex. But here's an individual who's blind, is not getting that visual input, and the brain is using that visual cortex to create a map of objects based on sound. And this is not seen in a control participant who tries to echolocate. So this is a great example of neuroplasticity, how the brain has used the visual cortex in a different way to accomplish this feat. And this is described in detail on page 255. I highly recommend you take a close look at that. I think sometimes when we read the books, we skip over these inset boxes, and this one in particular is really fascinating, really interesting, so please take a look at that.